This is the first section of the unit on sets. And what we're going to do in this section is introduce the idea of a set, define a set, describe the different ways we can write out sets, and a few properties of sets. We are going to define a set as a collection of objects, things, or numbers. Basically, these are going to be elements. So sets have elements, and these elements can be really any form. They can be a number, they can be a letter, they can be somebody's name, anything that you can collect together, I guess, as a unit and break it up into different elements. We call that a set. This first definition, the universal set, we'll talk about more specifically when we get the union, intersection, and complement. But for right now, the universal set is basically the set of all possible elements of the set used in the problem, denoted by a script U. Typically is the symbol they use to represent that, the universal set. Forgive me, I'm going to move this forward a little bit. Here are some example sets. So if your question is, well, how do you represent a set? Well, basically, one way to do it is just list the elements in squiggly brackets and separating the elements by commas. So, for example, the first set is essentially the set 1, 2, 3, 5. Those are the 5 elements. The next set has 4 elements: Ron, John, Mark, Phil. So it could be people's names. It could be states. The last set is Virginia, West Virginia, Maryland, North Carolina. Are your sets. Those are all examples of things in roster notation. If a set is in roster notation, all the elements of set are listed one by one and separated by commas. So, for example, 1, 3, 5, 7, 9 again. So really just kind of what we just did. You list the elements, separate by commas, and that's all you do with the squiggly brackets. We're going to learn 2 ways to describe sets. There's actually at least 3 I know of. There's also a descriptive form, which we will not use, but we will use builder. My bad. We did do roster notation. So roster notation was one way that we can describe a set. Forgive me, I lost track where I was at just for a second. Builder set notation is the way it is set up is you do X such that X and you give a description. So an example would be X such that X is amino acid. What I tried to do is think of an element that had a commonality, like there are these amino acids in chemistry you learn about, or biochemistry. I forget how many there are, but you could quantify them all together as a set, and you could describe them in, probably would be easier to do it in builder set notation, because if you had roster, you would have to write them all out. But that's the idea. So if you wanted to do, say, the state of Alabama, Arkansas, Arizona, and there's one more state that begins with A, but that would be your states that begin with A. That could be another way you could do sets. Another example of builder set notation. Alaska is the other one, forgive me. So Alaska, Alabama, Arizona, and Arkansas. Make sure I got that right. I have to write things down, but basically, Alabama, Arkansas, Arizona, and Alaska. So those will be the states that begin with A. So comparing the two, I made this little chart. And if that's too small to see, you can refer to, it's basically the same chart that is in your PowerPoint notes on D2L. Notice that I have the roster notation, and the set is A, E, I, O, U. And those are our vowels, so we could describe that as X such that X is a vowel. Or, for example, maybe your set was Huron, Ontario, Michigan, Erie, Superior. Those are all your Great Lakes. So you could do that in builder set notation as X such that X is a Great Lake. So that shows that some sets can be written in both builder set notation and roster notation. Interesting thing is if you have an infinite set, such as 2, 4, 6, 8, 10, 12, etc. Notice I put ... You can actually, if you can establish the pattern of the numbers, which we did, then you can actually just write down the pattern to where you know it's at, and then just put ... And that's a way you can represent a set in roster notation that's basically infinite. We can describe, of course, an infinite set in builder set notation by saying X such that X is an even whole number. So that's just some things that can be represented in both forms and the connection. And also, what if your set is infinite? Well, there's ways to even write those sets down. The last one I put question mark because I came up with a set of Greek letters that really don't have any connection. So, what do those elements have in common? Well, really, it's hard to tell. So we don't know. So that really can't be made in building that set notation, which raises the question: what are our limitations when we're describing a set? And I'm going to come back to that question in just a second. I do want to point one thing out because almost every year when I teach, and I try to throw a little bit of geography in there or whatever just to kind of make it interesting, like the Great Lakes, and just doing fun things with sets. Sometimes I get the students are worried that they're going to have to know all these geography facts or trivial stuff going into the test, and the answer is no. I will make it very basic if I ask a question like that. So don't panic about that. And our book even has fun little activities where you can do write, say, the 7 dwarves in roster notation. So, the homework assignment is you got to think of the 7 dwarves and then put them in a set form. But on a test, I'm not going to expect you to memorize all these trivial facts. So, just if it's something like that, it'll be very simple. Just wanted to point that out because that is a question I get in class sometimes. Typically, we do this early on in the year, and students are nervous about what they have to learn, and sometimes they're just a little bit precautious. So anyway, so my question was, what are the limitations in describing a set? Well, a set is well defined if the elements of the set are clearly defined. What that means is basically, as you can see I wrote down there, is there any confusion about what the elements are in the set? I could put an example up here. For example, if I wrote X such that X is a month that starts with J, well, that's well defined. We know what those elements are. It's January, June, and July. But if I wrote something like this, X such that X is a small dog, then we do kind of have some ambiguity, because what is exactly a small dog? And I might get varying answers on that. So, if it said a pretty dog, or, is a great tasting food. Anything along those lines where it's almost like an opinion, then it really, you don't really, that one person's idea of the answer will be different than somebody else's. So this is what they call a set that is not well defined, because there is this unclarity. Now, if I put more parameters, say, to that, if I said as a dog that weighs less than 10 pounds, for example, then you would probably be in the area where it is well defined, because that is something that would be more clear about what type of dog, you know, it's less than 10 pounds. You can kind of measure that, so that makes a difference. So anyway, that is just an example of, you know, something that is well defined, a month that starts with J as opposed to, you know, X such that X is a small dog. And sometimes you got to be careful. I guess a small dog can be defined by some weight class, say less than 20 pounds or something like that. But in this case, just using the word small is going to make it not well defined. Here's a little exercise that will go. And by the way, some of these, depending on the PowerPoint I have, I may not go for every example. I may leave some of those for you to kind of do test and practice. So in any event, in this first example, what we're going to do is determine if the set is well defined or not well defined. A is X such that X is a vowel, and I think that is pretty clear that that's well defined. We can list the elements A, E, I, O, U. B, X such that X is a river in Germany is also well defined, even though I would not be able to do that. I could list the Rhine, and that's probably about it. And the Danube, I think, goes through part of Germany. But outside that, I don't really know my rivers in Germany, but that's not the point. The point is that that's clearly defined, so that it's well defined. But looking at the last two, clearly those have some ambiguity or unclarity to what the elements are. For example, X such that X is a tall person, or D, X is a great tasting dessert. So those would be examples of sets that are not well defined. And by the way, and I'll probably mention this throughout these little presentations that I will post, is that if you have any questions, feel free to email me about this. I'm just trying to put together a short little video that might fill in the gaps compared to just reading the book or just going through my PowerPoints. This lesson is basically definitions. It's probably not as complicated, but doing some of the more rigorous sections, it probably will be nice. I can actually have the opportunity to, you know, work out problems and show you step by step what you have to do. Not so much the case in this section. Example 2, the question is to write the following sets in builder set notation. So my first set is Virginia and Vermont, which essentially is, you would probably say, well, those are the two states that begin with V. So I would describe that set as X such that X is a state that begins with V, or starts with V. The next one is, those are actually well, let me read them first. 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Those are your perfect squares between 1 and 10. And then the last one And I'll go back to B, and again, that when you're thinking about that, you're saying squares. Well, for example, 1 squared is 1, 2 times 2 is 4, 2 squared is 4, 3 squared, 3 times 3 is 9, 4 squared, 4 times 4 is 16, etc. Now, you probably will be familiar with exponent notation at this point if you went through the first unit on number systems. So, you've already kind of had some exposure to that. C, however, this is always an interesting one because some will figure it out and some try to get really complicated. But as you can see, they start with different letters. You have Utah, Iowa, and Ohio. And the fun thing about those 3 states is they aren't even close to bordering each other, so it can't be that. What it is it's just basically the only 3 states that have 4 letters. That's what it is. So it would be X such that X is a state with 4 letters. So I have the solutions there. Again, one thing you can, if you do miss something, you can go to the PowerPoints and look them up. Hopefully I can fill in some gaps by just talking about each of the slides. This is going the other way. So let's, well, how would you write the set in roster form? Well, Part A states that begin with with the letter O. There's 3 of them, and you would write Ohio, Oklahoma, and Oregon. Forgive me, I'm a terrible speller, but so far I think I've caught every error, if there has been one. The other thing is X, such that X is a state that borders Virginia. Those states are Maryland, West Virginia, Tennessee, North Carolina, and Kentucky. There's 5 of them. Like I said, don't worry about geography facts. I just kind of put that in as a fun activity. And of course, any homework or problems, you would have complete access to the internet. So certainly on your smartphone or on your computer, you can look them up. Anyways, that is going from roster form to, builder set notation to roster form. Natural numbers, these are just some important sets of, and these all deal with classifying numbers. So if you take 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., those are what you call the natural or counting numbers. So that is represented by capital N or script N. Script W is just the whole numbers. Now the difference between the natural numbers and the whole numbers is just 0. 0 is included in the whole numbers, as you can see. If we take the whole numbers and then add all the negative counting numbers, then we get what is called the integers, represented by Z. I can't remember the German word, but that comes actually from the Germanic roots, and they use the letter, the word representing integer in German begins with a Z. If you're wondering why they use Z, not I. Also, some important symbols. If you see the little symbol that looks like an E, and I'll write it here too, that means is an element of. So, for example, three is an element of the set 1, 2, 3, 4, 5. Or A is an element of the set A, B, C, D, E. If it's not an element of, they simply just put a strike through. And you're used to that notation. You learned in algebra that's equals, does not equal, it's just the equal sign with a line through it. So same idea, if you just put a line through it, it's opposite, so it means it's not an element of. Some other basic things about sets. The empty set is the set that contains no elements. The empty set is also referred to as the null set. If you guys watch World Cup soccer, if a team has a score 0, sometimes they refer to the score as nil. Same idea, nil, null meaning none. So, empty set. Symbolically, two ways to represent this set. One is by the Greek letter phi, or you can just do an empty set of brackets, either one. Okay. Let's just run through these. So example 4 says, is the following statement true or false? So if you look at the first one, A is an element, that's the way it would read, of A, B, C, D, E. That is correct, because A actually lies in that second set. And I probably didn't put much emphasis on that, but that's what that really means. So it's the idea of containment. So is A contained in the set? And the answer is yes. Now, I deliberately did a couple examples to test just to see how close you're paying attention to detail. So in B, it is A is an element of the set of A, set of B, and set of C. And this is actually not right. Because in order for the line here, you would actually have to have the set A. Which, if you look at part C, that's the way it's written. So if you're comparing B to C, C is actually correct because set A is actually one of the elements. So your elements in this set are actually sets. Whereas, well, it's the same one as B, but the difference is I have just the single element A, which is not the set A. Those are different things. So in order for that to work in this situation, you would have to have the set A. That sometimes can be a little confusing, but just think of this set as being a set of 3 elements, and each of them are sets. Each element of the elements of the set are sets. So in order to be an element, you would have to be a set. And then the last one is true. Basically, remember, capital Z is the integers, and of course 1 is an integer. I'm going to be very brief about this because I think it's pretty self-explanatory, and sometimes I may do that just to kind of shorten these videos because I don't know space-wise how much of an issue that's going to be. But trying to get the most important things down, I guess. But I briefly will mention these last couple of slides. This refers to equivalent sets. And for 2 sets to be equivalent, the only thing that has to happen is that they have to have the same number of elements. So, for example, 1, 2, 3, 4 and S, X, W, R, those 2 sets are equivalent because they have the same number of elements, each set containing 4 elements. So that was the lesson on sets. Again, email me if you have any questions, in particular distance ed students that may be watching these. So, the next slide show will be on subsets. But that is it for sets. Again, you know, these are on D2L. Feel free to go through and read through them. And also kind of, you know, work on the online homework as well as, problems in the book.